Hello. Hey, I got a question for you. Behind me is a rainbow. Anybody know the colors of the rainbow? With their eyes closed. There we go. That'll make it fun. Go, what?
Red, orange, yellow, green, blue, indigo, violet.
Great. The Roy G. Biv. These are all the colors that are capable of being seen by the human eye. Okay, now this is going to get real sciencey real fast, so make sure you're paying attention. You have different wavelengths of light coming into your eye all the time. Unless it's dark, then you have no wavelengths of light coming into your eye. But you have all these different wavelengths. Some of the waves look like this, some of them will look like this, but they all look different. This is what your eye is capable of seeing. It's capable of seeing the Roy G. Biv, or the red, orange, yellow, green, blue, indigo, and violet. Now, we get some weird stuff going on here. Colors are perceived very oddly by the eye. I'm sitting here and I'm looking at that light. Got it? So you can see what color light I'm looking at. I'm assuming that you can look at my face and tell that I'm looking in like the greenish yellow right now without any issue. And as I shift this way over here like this, I'm looking at the red light. And as I go this way like this, I'm looking at the bluish indigo side. Are we good with that? Okay, well check it out. When you look at light, that light goes in a little hole in your eye, bounces around on basically the nerve endings in the back of the eye, and it gets processed by the brain. And as you get over here, these are like the biggest wavelengths of light that your brain is capable of seeing. And rather than saying, wow, look at those big wavelengths of light, your brain processes it as red. That's what red is. Red are big wavelengths of light. Okay, so again, that gets processed as red when really they're just big. As I shift over here, I have medium wavelengths of light coming into my eye, and rather than saying, look at those medium wavelengths, your brain says, hey, greenish. And then finally over here, these are the smallest wavelengths of light that you're capable of perceiving with the eye. And again, rather than going, wow, look at those small wavelengths of light, you say, blue. That's kind of how it works. Now, some interesting things are going on. When your brain cannot perceive the difference between those wavelengths of light, in other words, you have them all coming at you at the same time. You got red, orange, yellow, green, blue, and they're not separated out, but they're all jumbled on top of one another. How does the brain perceive that? Because it can't discern between the different wavelengths. How does your brain perceive it? White. It perceives it as white. What will happen is your brain's like, orange, yellow, forget it, it's white. That's how your brain will actually perceive that. Now, we got some other weird things going on. Your brain, your eyes more specifically, are tuned to these wavelengths, kind of like you tune to wavelengths on a car radio. And what will happen is as the frequency, wavelength we'll say, as the wavelength gets smaller and smaller and the frequency goes up, you can see blue, and you can see indigo, and you can see violet until all of a sudden your brain can't perceive those waves anymore, simply because they're too small in wavelength. They're too high in frequency. Because of that, you see black, which I know sounds really weird. Do you notice over here, if you look, how many of you can see like a little purplish hue in here? Can you see a little bit of purple going on? Okay, do you notice how it does fade kind of to black? You see how all of a sudden, like, I see it real good, I see it real good, I see it real good, it's getting a little, and then it's just gone. This is a smaller wavelength of light, which is incapable of being seen. Does anybody know what the name of that wavelength of light, if you want to call it that, the wavelength of light is that exists over here, just on the other side of violet? Just curious. It's another color, if you want to look at it like that. What's the color you can't see on the other side of violet? Do you know?
Ultraviolet.
It's ultraviolet, which basically means super-duper violet. Okay, so what they call it, ultraviolet. And it exists right over there. By the way, there are frequencies of wavelengths that are smaller and smaller and smaller hanging out over here that are even stranger. Okay, for example, you have like radiation, gamma radiation, all those things hanging out over here. Ultraviolet radiation that causes skin cancer. In fact, all of these, as I hang out over in this area, are dangerous. They pack a punch. They can actually harm your body. Luckily, there's not many of these frequencies emitted by that light, so we're okay. Probably a little bit of ultraviolet, but not much. All right, let's journey the other way. As we're going this way, the wavelengths are getting bigger and bigger and bigger and bigger and bigger and bigger, and oh. Your brain can no longer perceive those because the wavelengths are too big. So just like over here we had violet and ultra super duper violet, over here on the other side of red, you can see that fade real well. Check it out. See how it fades? As it fades out like this and your eye's no longer able to perceive it, you have super red. No. Ultra red. No, what do you have?
Infrared?
You have infrared, and that's something that you've probably heard of also. So your eyes are tuned to these frequencies. Just like your stereo in your car can go down to 88.3 for a frequency, your eyes only go down to, for frequency, let's see if we go this way, your eyes can only go down in frequency to about here. And they can only go up in frequency to about here. Just like that, photosynthesis uses light from the sun. Light from the sun is white light. It's got all the wavelengths, including ultraviolet and infrared and gamma rays and radio waves and microwaves. It's got all kinds of stuff. But evolution has basically made it so that we have two major pigment absorptions. In other words, these wavelengths of light right here are really good at making photosynthesis happen. The energy in this frequency right here can make photosynthesis work. The energy right here in these frequencies are also very good at making photosynthesis work. In here, not so much. These do not, the greens actually do not. Isn't that kind of weird? Because when you think of chlorophyll, you think of green. Believe it or not, this is really good at causing photosynthesis to happen. This kind of stinks at causing photosynthesis to happen. And then it picks up again over here. End of the story, or moral of the story, is that's why leaves appear green that have chlorophyll. What? This is used for photosynthesis very, very well. This, not so much. This is used for photosynthesis well. And that's the reason why leaves that contain chlorophyll are green. Now, some of you have your hands in the air because it seems like you want to explain that a little bit. So, Mr. LeGros, why don't you go for it?
I'm guessing it's because, like, since those other two colors, like red and blue and violet, are used for photosynthesis, that the green is used to make the pigment, the chlorophyll, like it reflects that color on the chlorophyll.
There it is, right there. That concept of reflection. This is called an absorption spectrum. And over here, these colors are absorbed and the energy is used. In here, the energy is simply reflected back towards your eye, which is why you say, wow, look at those green leaves. And then these colors, yet again, are absorbed. So your absorption spectrum, I'm going to draw red on red, see what it looks like, will look something like this. Photosynthesis works well over here. I should have just used black. Let's try that again. Photosynthesis will work well over here, drops off in here. These are the colors that are reflected back to your eye, and then picks up again over here like that. So if you ever hear somebody discuss an absorption spectrum, which is one of the first things we'll be talking about, that's what we're talking about. Learn more at www.phasescience.com.